So this is a short video on something you learned a long time ago, which is what is called a heating curve. Okay, for this substance, hopefully you can see it would have a melting point. I'm really just reviewing stuff. Hopefully, the melting point would be equal to about looks to me like 50 degrees Celsius. Make sure it could. That's also the freezing point, right? Because it's just a temperature. The boiling point, right, would be the temperature at which it boils, which is also the condensation point, which is equal to about, I think it's 110 degrees, if I'm reading this correctly, Celsius. Now, let's talk about these segments a little bit. This segment here can be used to determine the heat of fusion and the heat of vaporization and their relative amount of energy. So let's just assume that we're adding heat at a constant rate. Let's say we're adding 100 joules every minute, and we have, let's say, a 10.0 gram sample, right? And we'll say, well, what is the heat of fusion? Now, first of all, make sure it's clear. The heat of fusion, which is to melt, is the same amount of energy as the heat to, there's no name for it. I'll call it heat of freezing, because there's no term for it, but the amount of energy required to melt, the amount of energy required to freeze will be the same. We can figure what that is because we could go, okay, it took 1 minute, 2 minutes, 3 minutes. So it took 300 joules to melt our sample. If our sample is 10 grams, it took basically 300 joules to melt, 30 joules per 1 gram. And that will be our heat of fusion / heat of freezing. The only difference is whether energy is going in or out. Now, usually heats of vaporization, which is this segment here, are larger, and usually actually a good deal larger. It takes a lot more energy to usually turn something into a gas or vice versa than it is to turn something from a solid to a liquid and back. All right. So in this case, it took 1, 2, 3. It took 4 minutes. So our heat of vaporization would be 400 joules for 10 grams, or 40 joules per gram. Yeah. Specific heats. All right, just a quick review of these. Okay, so how can we determine the specific heat from a graph? Well, quite easily, actually, because what we have is we have a amount of energy, right? So specific heat is joules per gram per degree Celsius. And remember, if it's a small value, that means it takes very little energy to raise its temperature. So you've got a solid, a liquid, and a gas on this thing, right? And what you really want to notice here is you want to notice the slope, right? So the L has the lowest slope, which means it's going to actually end up having the highest specific heat capacity. I'll repeat that. The one with the lower slope basically took more energy, took more time, and time in this case equals energy because we're adding heat at a constant rate, okay, to raise its temperature by whatever number of degrees. And we can actually calculate that using the information on the graph. So I can go, okay, the temperature went from 50 to 110, so it went up by 60 degrees Celsius. That's going to go on the bottom, right? Because that's down here, right? And we have a 10 gram sample, right? And the time it took for it to do that temperature change was 1, 2, 3, 4. It took 5 minutes. So it took 500 joules. And if we take that, we do a little math with that, we can actually get the value. So basically, we get 50 divided by 60, because I'm just going to cross out. This is basically 500 divided by 600. I'm not even going to reduce that. Honestly, I don't have my calculator with me here, so it's joules per gram per degree Celsius, right? Whatever 5/6 comes out to, which is going to be like 0.8 something. So this is going to come out to 0.8 something. I'm assuming. I think I'm right. Joules per gram per degree Celsius. If we look at a steeper portion of the graph, like we look at this segment over here where it's a gas, right? We'll find that the specific heat will be a smaller value. So instead of, basically whatever 5/6 is, okay, we should get a fraction that's less than 5/6. All right. So let's see, we have it going from 110 up to, it appears to be 180. So it's changing by 70 degrees Celsius, right? But it looks like it's only taking about 2 minutes to do it, so it's 200 joules, right? And again, you get the 10 grams there. Now, I'm not even going to bother with the math, but I know that 200 divided by 700 is definitely smaller than 500 divided by 600, right? So this is like 1/3, maybe 2. That's somewhere in the 20% range, probably, something like that, maybe the 15s. I would need a calculator, I'm not going to bother. But that's joules per gram per degree Celsius. And clearly that's a lot smaller. I'm going to put approximately equal so my video is legit. Clearly a lower specific heat capacity. And with that, then we could figure out anything for any sample, because we could go back and use our MC delta T formulas and our MHF formulas and our MHV formulas And we could, once we have these values, we could then use them and say, well, what if we had 15 grams? How much energy would it require to melt? Or how much energy would it require to boil? Or how much energy would it require to go from here, this temperature right here, all the way up to here? In this case, we'd use MC delta T once, we use MHF one time, and we use MC delta T again and add up the total amount of energy loss or gain in all those three processes.